On this Cartesian plane, we have a line. Now, when you were doing CSEC, you learned that the equation of a line is given by y is equal to mx plus c. Now, what we're going to focus on here is m. We are going to be focusing on m. M here represents the gradient. So before I show you how to calculate the gradient, we're going to be looking at what this gradient actually is. And so what m is, the gradient, it's a number, a constant, that is going to be telling us how for every unit of change in x, how does y respond. So every time I change the value of x by 1, whether I put it up or down, every time I change it by 1, how does the dependent variable y respond? Does it go up? Does it go down? Does it stay the same? And if it goes up or down, by how much does it go up or down? So, for example, if I were to be, say, if I had a dependent variable that is recording the weights of people, and the independent variable would be some weight loss pills. Now, I'm wondering, how does an individual's weight respond to the number of pills that they take? If I were to plot the relationship between the number of pills an individual takes and their weight, and I end up getting a line like that. If I were to get a gradient of, say, 2, that is telling me that for every pill that this individual takes, for every pill that an individual takes, their weight is actually increasing by 2 units. However, if I were to get a gradient of -1/3, for example, what that would be telling me is that for every unit of pill that an individual takes, their weight falls by 1/3 of a unit. So in other words, what we're saying is a gradient of m is telling us in effect that for every 1 unit of change for the independent variable, the dependent variable changes by m units. And we will know the direction that it changes by the sign of the gradient, whether it be negative, as is the case right there, or positive, as is the case right here. Now, what I want you to take note of is the fact that, again, let me draw a line. And what I want to show you is that the gradient of a line can be found a number of ways, but my personal favorite way of finding the gradient, which I will continue to call m, is by taking 2 points on the line. Let's say here we have x1 and y1, and up here we have x2, y2. The gradient of the line is found by taking any 2 points and following this formula: y2 minus y1 over x2 minus x1. Now, what this is implying to us is that if I were to take any 2 points, when I say any, I mean any 2 points on the line, if I were to take any 2 points on the line and find the gradient between those 2 points, no matter how close they are and no matter how far they are, as long as I take 2 points on the line and I find the gradient using those 2 points, I will get the same number. In other words, for a given line, the gradient is constant. The gradient is set for a line. So now that we've come to appreciate fully what the concept of gradient is, what we're going to be looking at now is an application of the concept of limits. So as we said, the gradient m of a line is telling us how for every unit of change in the independent variable, how y responds, the degree and direction to which y responds to this change in the independent variable. A nicer way to say it is by saying it's the rate of change. It's the rate of change of the independent variable y with respect to x. That's a nicer way of saying it. And so we now know how to find the rate of change of y with respect to x between 2 points. And you on a line, finding the rate of change between any 2 points, as I said before, will always give you the same answer because the gradient is constant for a line. However, let's say that we have a curve, right? Let's look at this curve. And what we want is to find the rate of change at a point. Let's say, for example, right here. Now, you see, for a curve, unlike a line where the gradient at every point is constant, or the gradient between any 2 points is constant, it's not the same for a curve. The gradient at this point here is different from the gradient here and here and here. The gradient is different at, for the most part, we could say almost every part of the curve. But we want to find the gradient at a point, right? We want to find the gradient at a single point, and this point we will call it a f of a, right? So let me put it in bracket right here, a f of a, right? Yeah, so that's what we want to find. So we want to find the gradient at that point. So let's draw a tangent to that point. Let's imagine that line actually touched the curve. See? Yeah, it touched it. Yeah, not drawn very well to scale, but yeah. So here we have this line. But the thing is, the only point we know on this line is this, a f of a. But in order to find the rate of change, we need 2 points on the line. We need to know at least 2 points on the line in order to find the rate of change at this point, at the point a f of a. So what is happening here is that we don't want to find the rate of change between 2 points. What we want to find is the rate of change at a single point, a f of a. So we're going to call that the instantaneous rate of change. And in order to find that now, let's see if we can do a little trickery. So what we're going to do is that we're going to say, okay, we're going to take another point, right? This point will be, let's say this is x, and so let's say this is f of x, right? And what we're going to do is that we're going to draw a line that passes through a f of a and through x f of x, right? Now, if I were to say that the gradient of this line is equal to the gradient of this line, would that be true? No, that is not true. That would not be true, and that would be a presumptuous assumption. So what do? What I'm going to do is that I'm going to say, all right, I am going to keep bringing this line that passes through the point a f of a and just bring it closer to the point a f of a. Just bring it closer to this line. So we are here getting a number of lines that pass through the point a f of a, and they pass through another point on the curve. So we can easily find the gradient of those lines. So what we're going to do now is that we're going to say, all right, To find the gradient